I think we're about ready to get started on the next round of sessions. And starting us off is Zhihui from the New Jersey Institute of Technology. And go ahead and take it away.
Hello, I'm Zhihui from AGIT. I'm glad to present our work on how to do large-scale graph analytics in Arkouda. The major object of our research is provide user, especially the non-HPC user, a one-stop solution so they can handle very large data set. Our research focus lies in two aspects. One is the data structure, another is the corresponding algorithm. Our method was based on an open source framework, Arkouda. So why Arkouda? Here are the slides from the co-founder of Arkouda, one from Mike, another from Bill. The left slides show that Arkouda can provide both the flexibility and the high performance. And the right side show that we can extend Arkouda in different way. You can extend it in Python or in Chapel to make Arkouda much powerful and meet more requirement. So in my opinion, the left slides shows the basic or the important function of Arkouda. It's that it can provide us flexibility and high capability. About the right slides, it shows that how we can extend Arkouda to meet our requirement. So we can say that Arkouda is a very vital system. It can grow to meet more and more requirement, become much powerful than before. So we use Arkouda to do our graph analytics. First, why we will support graph in Arkouda? This is because graph is a very powerful tool in our real life. The social network, the web, so many things can be abstracted as a graph. And the real world graph has become very, very large. Analyze such graph is a challenging task for us. So this is the reason why we select graph. What we have done in this research is that we develop a double index data structure to support graph. At the same time, we use Chapel and develop parallel and distribute best first algorithm to support basic graph analytics. About the first aspect, our graph data structure. The major advantage of our data structure is that it can provide constant time to search from given edge ID to find its vertices. At the same time, given the vertex ID, we can use context time to find its adjacent list. So this is a very important advantage of our graph data structure. We have two index array, just show as the right figure. One is the edge index, one is the vertex index. Use the two for giving edge. We store its starting vertex and vertex in the source array and destination array. This is edge index. For the vertex index, for given vertex, we can find its adjacency list in the edge index array. For example, here for X, we can see that from 1,000 position, it has 3 neighbors. This data structure has some similarity with widely used CSR data structure. We can see that our SRC and destination array has the same size, very similar to the value array in CSR. And our start array has the same size or very similar to the column index array in CSR. And our neighbor array is very similar to the row index array. This is their similarity. But the difference is that in CSR, it cannot search from edge ID to the vertices. The main difference. But our method, we can do this kind of search in constant time. This is our advantage. But the disadvantage is that our data structure will need another array to store the vertex information. This is the difference of our data structure with CSR array. Based on our data structure, we provide an edge-oriented graph partition method. The basic idea is that for a very large sparse graph, and the degree of each vertex is very different. If you partition the graph based on vertices, this will cause very serious load balance problem. So we divide the graph based on edge. So in this way, the edge are equally distributed on different parallel resources. But we align the vertex with the edge. In this way, for the different kind of graph search can maintain the load balance. This is the advantage of our method. About the algorithm, the BFS algorithm, the basic idea is from the given root ID, you first search the node with direct edge to the source ID and always form a new frontier. Based on this frontier, we'll search next frontier. This is the basic idea of the BFS method. Here is a graph source vertex to search level by level on the whole graph. So this method is the typical or standard BFS method from the frontier to next from the current frontier. Each element in current frontier can search in parallel to get the element in the next frontier. This is a basic idea of BFS. About our BFS method, we call it high level. We have developed 2 versions of the BFS method. One is high-level BFS method. High-level means that we will use high-level type of data structure. Here we use distribute bag to hold the current frontier and the next frontier. Then we use code for all parallel data structure to realize, to implement the distribute parallel computing. Then for each current frontier, we will parallel search to build the next frontier. This for all. This is what is done by this for all. At the same time, for each vertex, when it finds a new vertex, they can add to the next frontier in parallel. So this is the basic structure of our method, high-level BFS method. You can see that we have 3-level parallel computing method, from high level to low level. So our method can explore the hierarchy parallel methods of BFS in this way. This is our high-level method. After we develop this machine, I rewrite a low-level machine. I think how to further improve the performance of this machine. So I use the array to replace the high-level data structure of CHIUW and rewrite this BFS method. And I write explicit communication method and try to improve the performance. This is our low-level method. But the basic framework is the same. Then we test the performance of our method. We use different kind of sparse graph to test our BFS method. The performance includes 2 parts. One is how to build a graph. Another is how to do the BFS. For the first part, we can see that in Arkouda, the building efficiency is almost the same, which means that for the given graph, if you increase the number of edges, the building time will increase in linear way. This is the building method of our BFS algorithm. Another is algorithm, the BFS algorithm time. We implement different kind of BFS variances. We use not only use dist bag, but also the set and the domain. We use both for all and the code for all to compare the performance. And the result is very interesting. For example, in MPI program, we often see that redundant computing can achieve better performance. But here, redundant calculation, even it can avoid idle threads, the performance is worse than the non-redundant calculation method. This is one reason. Another is that parallel construction, the for all and the code for all. We can see that for different at a different scenario, the performance is also very different. A very interesting result or unexpected result is that our low-level method, I think the performance should be better, but the result shows that our low-level method cannot beat the high-level algorithm. This is a very interesting result. It also shows that the chapel can achieve much better, very better performance. Here, we also optimize our method to use the reverse pre-processing step. In this way, we can increase the locality of the graph. In this way, we can see that after we use this RCM method, almost all the method can achieve better performance than before. This is one of our optimization method. So the conclusion is that Arkouda can really handle very large graph. It can provide both high productivity and high performance. And the chapel-based method can achieve very high performance, even better than the low-level method in our case. This work just our first step to evaluate the ability of how to extend Arkouda to support graph analysis. We will do more graph algorithm and do more optimization in future. Finally, we will thank Brian, Alec, Engine, David, and the chapel community. We will integrate the algorithm into Arkouda. They provide very useful, very important help for us. At the same time, our work is supported by ASF. This is my presentation, and I'm ready to take your question. Thank you.
Awesome. Thanks for the presentation, Zhihui. So it looks like we've got a couple of questions here. Brad asks, what are your main pain points when using Chapel? Or what more could Chapel be doing for you that it isn't currently?
Oh, I have long programming experience in MPI, but we are using Chapel. The basic idea is same. It's good, but the difficult for me is that Chapel is very complicated. It has very powerful function, different kind of functions. Mm-hmm. I often need. For example, I need one function, but I need a long time to find what the exact way to express, to use it in Chapel. This is my difficulty to use Chapel.
Mm-hmm. Okay, interesting. Yeah, I'm sure there's more. Is it more an issue of like figuring out how to write it, or is it a way of like finding it in the documentation for something that you know already exists, would you say?
Sorry, I didn't catch your question. What it's about?
Was it more an issue of the like documentation for a function that you already knew was around not being able to like search it appropriately, or was it hard to like create the prototype for the function itself that you were thinking? In my experience, at the first I use Arkouda, how to learn the framework, the basic framework to implement your idea. You need to know so many details to implement your idea. The basic idea is very simple, is very clear, but how to fit your idea into Arkouda, the Chapel. This, I think, this is the major problem Okay.
Yeah.
And then I think one more question since we started a little bit late for your session. So Brad also asks, Graph 500 also uses BFS to his knowledge. Any idea whether a chapel-based entry could compete with current leading or traditional entries?
I don't think our current version can beat the top level Graph 500 version. And we are trying to optimize the current version in the future because based on my experience, it seems that there are very different kind of details. In chapel programming, the difference may be very small, but the performance can be very different. This is my result, my experience to do chapel programming and the performance comparison. Yeah.
Okay. Well, thank you very much again for your presentation.